In the single second it takes for your heart to beat just once, this incredibly complex cascade of events happens. We're going to break down that entire journey, from the very first electrical spark to that final, powerful squeeze. It all starts with a sound we've all heard our entire lives, that classic lub-dub, lub-dub. But what's actually making that noise? Well, those sounds are the story. They're the sound of powerful valves slamming shut. And by the end of this, you're going to know exactly which ones are which and why. I want you to think of your heart as this amazing, tireless factory. It's got an input, that's the blood coming in from your veins, and it has an output, the blood going out through your arteries. And get this, it's so unbelievably efficient that it pumps your entire 5-liter blood supply all the way around your body every single minute. It's just a relentless, perfect machine. Okay, so to really understand how this factory works, you only need to know its two fundamental modes. It's the basic rhythm of the entire process: a squeeze and then a relax. And here they are. Systole is the squeeze, right? The phase of contraction. And diastole is the phase of relaxation, when the heart's chambers get to fill back up with blood. Squeeze, relax. Systole, diastole. Every single thing that happens in one heartbeat falls into one of these two phases. It's that simple. And that's really the whole idea. When we talk about the cardiac cycle, we're just talking about the complete sequence. One systole and one diastole that takes us from the beginning of one lub all the way to the start of the next one. But wait a minute, what tells the heart muscle when to squeeze or relax? Before any physical movement can happen, there has to be a command, right? And that command? It's an electrical signal. We can actually see this electrical command mapped out on an ECG, an electrocardiogram. And each little part of this wave tells a story. That little P wave at the start, that's the signal for the atria, the top chambers, to contract. Then you get that big QRS complex. That's the massive signal telling the powerful ventricles at the bottom to contract. And finally, the T wave shows the ventricles electrically resetting or repolarizing, getting ready for the very next beat. You have to remember this one thing. Electricity always comes first. Depolarization is the electrical command that says contract, and repolarization is the command that says relax. The electrical signal is the boss, and the heart muscle, it just follows orders. Okay, so the electrical orders have been sent. Now let's watch the mechanical pump spring into action. This is the physical process of actually moving the blood. The mechanical cycle has 4 key steps. First, the atria give a little squeeze to top off the ventricles. Then, we hit this really critical phase, isovolumetric contraction. Now, isovolumetric sounds fancy, but it just means same volume. The ventricles start squeezing like crazy, but all the doors, the valves, are shut. This builds up a ton of pressure. Then, the exit valves burst open for ejection. And finally, isovolumetric relaxation, where all the valves close again as the ventricles relax and the pressure just plummets. And wow, this chart just brilliantly illustrates the difference in power. The left ventricle, which has the massive job of pumping blood to your entire body, generates a huge 120 millimeters of mercury of pressure. But the right ventricle, which only has to pump blood next door to the lungs, it only needs about 25. That's exactly why the muscle wall of the left ventricle is so much thicker. Okay, 2 final concepts that basically decide how hard this pump has to work. First is preload. Think of it as the stretch on the ventricle right before it squeezes. It's all about how much blood has filled it up. And then there's afterload. That's the resistance, the pressure the ventricle has to push against to get the blood out into your arteries. So, we know how the factory works, but how do we measure its output? Let's forget all the confusing medical terms for a second. I'm going to use a super simple analogy to make this all crystal clear. First up is something called end-diastolic volume, or EDV for short. This is just the maximum amount of blood the ventricle is holding at the very end of its relaxation phase, right before that big squeeze. The chamber is filled to capacity. So let's just imagine the ventricle fills up with 10 apples. That's it. That's our end diastolic volume. It's the total amount we have to work with for this one heartbeat. Next, we have stroke volume, or SV. This is simply the actual number of apples that get pushed out of the heart during that single squeeze. So with that powerful contraction, the heart pumps out 6 of those 10 apples. Our stroke volume for this beat is 6 apples. Simple as that. Now, this is a really key point. The heart doesn't actually empty completely. There's always a little bit left over after the contraction. We call that the end systolic volume, or ESV. It's just simple math, right? We started with 10 apples, and we pumped out 6. So that leaves 4 apples behind inside the ventricle, That's our end systolic volume. It really is that straightforward. You see, now that you get the whole Apple thing, these formulas are a piece of cake. Stroke volume is just what you started with minus what you have left. Ejection fraction is just the percentage you pumped out. In our little story, that's 6 out of 10 or 60%. And cardiac output, that's just the volume you pump per beat times the number of beats per minute. That's the whole shebang. All right, it is time for the grand finale. We're going to take everything we just learned, the pressures, the volumes, all the different phases, and put it all together on one single elegant graph that tells the complete story of one heartbeat. Just look at it as a journey, a little racetrack for blood. We start at the bottom right as the ventricle fills up. See how the volume goes up, but the pressure stays low? Then boom, we shoot straight up. That's isovolumetric contraction. Pressure skyrockets, but the volume is constant. Next, we move to the left as the aortic valve opens and blood is ejected, so the volume goes down. And finally, we drop straight down. Isovolumetric relaxation, pressure plummets. That complete loop, that is one perfect, powerful heart. So, from the simple lub-dub to the electrical command to the powerful mechanical squeeze, all of it is captured right there in that one single loop. Your heart does this over 100,000 times a day, every single day of your life, without ever taking a break. It really makes you stop and wonder, what else in the known universe is capable of that kind of perfect, relentless work?